Okay. And yeah, just kind of clarify. So someone just starts the videos like, what's going on? You were just talking about, CNNs and like, saying like how this is used. And I mentioned how you can use like convolutional neural nets for like speech recognition, like in a spectrogram. So let me go ahead and show you what that looks like. Here, I'll share my screen. um, and this is a little more informal than us being like a specific lesson, but that's okay. It's just two of us. All right. So yeah, I mentioned how you can basically take CNNs. Usually we talk about, I actually talked about this in my notebook, what like CNNs are good for and stuff like this, what you probably learned with Jeff last time. But usually we associate with like computer vision, like I mentioned, but you can like do a whole bunch of things. And the real reason why is because convolutional neural nets, like the whole point of them is to find patterns that are close by each other. So like the idea is that let's see here, like data that are quote unquote close by each other are related in somehow. And this is different from like what I usually do if I introduce CNNs is I kind of show neural networks. You can take a neural network, no CNN, just a basic neural network, fully connected neural network that we've kind of talked about. And you can actually try feeding in this image into a neural network and do all right. But when the image starts getting more complicated, it's hard to tell. And convolutions, like where you talk about like this kernel, this convolution basically allows us to kind of say, well, these things in this area are related together. So that can translate into speech recognition. So we can actually do something called a spectrogram. And you can see an image right here of a spectrogram going on. I actually think there might be some more images. But basically, it's like I said, it's a visualization of kind of like frequencies. It's really like a Fourier transform, if you're familiar with that mathematically. Yeah, it's really interesting. So the idea is that you take like, instead of frequencies, like you can picture, if I said like, think of like what sound looks like. Oh, there's a good picture right here. It looks like this. A Fourier transform basically plots them out and saying, oh, instead of saying over time where the frequencies occur, they basically show where those frequencies and it reformats it, which is really interesting. That's more or less kind of like what's going on with a spectrogram. But the idea is basically you're plotting out all these like frequencies, and you can imagine, like, I'll use English since we're speaking English, is that when English, we have, when we say, I'm gonna just grab a random word, spectrogram. Well, you think about that, when you say spectrogram, it goes spectrogram. Like there's kind of like different parts. So it's not really letters. We call these phonemes. So this is kind of like mixing, we're putting everything together right now. CNNs, natural language processing, all this. But when you say stuff like spa, like that, that's called a phoneme. Basically, it's kind of like isolated kind of like sound. So it's kind of like the letters of speech, if that makes sense. And there's actually like a whole bunch of like linguistics you can talk about of saying human speech and saying like what different phonemes. Some phonemes exist in languages that don't exist in other languages. And then there are even phonemes that aren't like, they're theoretical, but like no one does them kind of deal. That's a whole different kind of story. But the idea there is that you have like, when you say spa, the next word that's you're speaking, like the next phoneme really matters. So that closeness, that related data, it's actually really important. It's not a separated like entity. And so you can think of that as like, oh, well, those are patterns that are very closely related. Like they're not just like, they're like close together. And that's where it's kind of hard for me to say like I can visualize like, oh, visually close together. But you can think of like things that are like, they're related together because they're spoken close together or their location or other things like that. That's where CNNs go like, hey, CNN's like, we can do this stuff. So you actually would take this spectrogram and actually use a CNN to help detect parts, and you can actually use that for speech recognition, which again, really cool. What's also really cool, which we'll talk a little bit today, right, is transfer learning with this, is that you can actually take something that's very different from the original source material, train it on this thing, like let's say a CNN, and you train that really, really well, and it does a really great job. And then you can transfer that knowledge, essentially, that process, to something that's actually very different. And you can actually get very, very good results. So we'll talk about that today. Also, sorry, this is kind of off topic. I've never seen this far. I know Chrome Music Lab. I wonder if they have a spectrogram now. Oh yeah, I know this one. So like, I don't know if you could hear that harp play for a second, but if you hear like, this is like different things. And basically it's just showing different like frequencies. So that's kind of like what a spectrogram does. I like Chrome Music Lab. They have some really great visualizations for, it's more for kids, but they actually have some great visualizations of like sound and stuff like that. So that's a really cool one.
Yeah, so sorry, quick question. And
yeah,
I do apologize if it's a lot of noise and wind.
You're okay.
Weather's starting to pick up. But so with a lot of machine learning,
Mhm.
will the information be transformed first into visual representation, then analyzed, or is a lot of it just whatever comes in the form of like matrices or tensors?
Yeah, that's actually a good question. It's actually, you're saying the same thing. When we do a visualization like a spectrogram like this, like you can think of it like we as humans are probably thinking of it like, oh, spectrogram, there's that picture. But really that picture is represented by a matrix of numbers, of basically a bunch of vectors and stuff like that. So really all data, like all neural networks care about, it's like they want numbers of tensors, basically. They just want tensors. And we can take an image and represent it with a tensor, or we can take, sound and represent this with a set of numbers. And a spectrogram would be one way to essentially do feature extraction. You're saying, here's the raw data of sound. We know kind of like what the sound is, and transform this into basically a tensor that we know how to do process on. And the analogy is that we know we can make a visualization. So we can see patterns in this visualization. It's not so much that like we make the visualization and then the CNN would look at that visualization. It's much more like we're transforming our raw data into a format, which is just essentially tensors that a CNN can look at. And when I see CNN, it could also just be a neural network too, since neural networks really just taking vectors. So yeah, it's kind of, it's useful to use this as being like, oh, it's a visualization, and then we can use a CNN on top of it. But it's more accurate to say, oh, we transformed it into numbers, into a different set of numbers representing the same data, and using that format to figure things out. So this kind of emphasizes a little bit of like a big part of just neural networks or machine learning in general is it's not so much about what the model structure is by itself, although that's a very important part. A lot of times you can get a lot of bang for your buck by getting the right feature set. If you can extract proper features from it and then feed it into a model, that might do loads better than trying to get a really complicated model. And that's because, like, for example, a deep learning, neural networks can basically be designed to make any function you want. However, that might be a very, very complicated neural network, which might not be really realistic to train. So those feature sets are kind of like useful. I'm kind of jumping around a little bit. I hope you don't mind, because I usually teach this set of course kind of like in a different order and kind of string them together. But I have a example of a neural network, and I'm trying to remember if I have this in here. There was an example I gave. No, it's not here. I have an example of a neural network that that I built based on this kind of. I wonder if it's in there. Based on this programming problem called fizzbuzz. Have you guys heard of that? Have you heard of fizzbuzz before?
No.
Okay, so fizzbuzz is a really basic programming problem. It's a little bit of a game. So the idea is you count from 1 through let's say 100, right? And you say like 1, 2, 3, and then if you hit a number that's divisible by 5, you say fizz. If you hit a number that's divisible by I think it's usually 3 and 5. So it's like if you hit a number that is divisible by 3, you say fizz. If you hit a number that's divisible by 5, you say buzz. And if it's divisible by both of those, you say fizzbuzz. So it would look like 1, 2, fizz, 4, buzz, 6, 7. Oh, I messed up 6. So 6 would be fizz, then 7, 8, fizz, buzz, because it's 10, right? 11, 12. Well, 12 would be fizz. So you can see you can kind of put these things together, and then you hit 15, you say fizz buzz. So it's he's like, oh, and the programming question is like, go ahead and program this out. So it turns out that's actually, let's see if I can find it real quick. Like a really basic programming problem. There was kind of this interesting article that came out, like a little blog post about a few years ago, where someone that was given a data science machine learning interview, or just an interview, and basically said, code up this fizzbuzz question. He's like, this is a really basic question. He said, okay, let me go ahead and try to basically use neural networks to do this. It's not a real interview, but it's kind of like you could see this going through. And so I actually tried implementing this because I thought it would be kind of fun to try out. And what's really interesting is that it turns out the features that you need to put in here, you can get a really big neural network trying to figure out if it's fizzbuzz or fizzbuzz. But it turns out if you give the right kind of features, whether that's like a decimal representation versus a binary representation, it turns out the features themselves actually do a big job. And turns out if you give the right features, and the right features would be is this number divisible by 3? Is this number divisible by 5? You could perfectly solve it. So that's kind of the idea of like, if you have the right features, you can actually like have a lot more like success with your neural network or your machine learning model. And I think that's something that sometimes we kind of forget about, because it's really exciting to try, you know, a really complicated neural network or a really complicated algorithm and pushing it through. But yeah, that's kind of a good offset. But yeah, go ahead.
Oh, so that's why so I was reading this section and I ran into this portion. It seemed a little unclear to me, because what the curriculum spoke of was with regards to feature extraction and fine tuning.
Right.
So this is kind of where like those two techniques would be really useful in CNNs, in that they take the pre-trained network, depending on which one you use, freeze or unfreeze the weights, and in an attempt to try and pull out the most influential, the most impactful features, then use those to run your pre-trained network that was trained on general data and this specific part, and then try to make an accurate prediction off of that.
Yeah, I think this actually relates a lot. Last time, I think I have the recording up for NLP, right, for section 49. So if you haven't gone through that, I think that might be kind of useful in the sense, and that's really why feature extraction for NLP is so useful. It's like, if you can pull out these right features, you can make a pretty good, like, you know, model to make those predictions and stuff like that. And the one that you're talking about for the curriculum, building up those feature extractions, I call them bottleneck features. So we'll talk a little bit about that too, like what that looks like. But the idea too is like the CNN, which is already pre-trained, is kind of part of transfer learning. It's already pre-trained on some data set, and you give it some new data, it would produce essentially a set of vectors. And well, I should say a vector for that image. And with that vector, then you can go ahead and take that and train from it. And the reason why that happens, I'm kind of jumping all over the place. Let's see if I can find it really quickly. I have, this is all from my repo that you can find if you need to, but nope, that's not it. It's visualizing CNN parts. Okay, is that convolutional neural net? This is actually comes from, I think, Karis actually talks about this in a blog post, but you can think of these like each part of the convolutional neural net. So if you remember back, like this is kind of like the beginning of the convolution, the CNN, and it moves forward, you know, out through here through different layers. Like this is a convolution, another convolution. You might have many, many convolutions, and then finally the fully connected neural network. You can actually do visualization, which I think Jeff might have talked about. The curriculum kind of talks about it, but you can visualize each filter essentially, or these parts of the convolution, which is like a set of filters. And you can see that at the very first part, this is the very beginning of the convolution neural network, is kind of like very basic patterns. You can see little spots, little kind of like stripy kind of like, you know, structures. You can see more kind of like horizontal versus diagonal versus, you know, kind of more of these parts. And then as we kind of go deeper into this convolutional neural net, trained on, in this case, this was trained on ImageNet, which is a huge amount of data sets, you can actually see it build up much more complicated, you know, extra features. And you can, in fact, like, depending on your data set, for example, data sets that were trained like on animals, you start seeing in this kind of layer more like fur and whisker and eye kind of like structure and features and stuff like this. And so the idea, what you're talking about, like feature extraction, like from the curriculum, you would feed in, like you would train this network so it would get to this point, right, with these filters. Then you would take, like, let's say, so a good example I have is there was a paper that was done about detecting skin cancer. And, you know, like, you know, skin cancer has these weird shapes and colors and stuff like that. And the idea of it was to see if you can take a picture of skin cancer and determine if it was malignant or not. So is it going to be something we need to look out for, or something that we can just ignore? It's just like a mole or something like that. And it actually did did really well. Like, I think it was up at human level or surpassed human level, like professional dermatologist level detection. So it did a really great job. The way they did it was they actually trained it. The model they used was already pre-trained on detecting on like images, like things of like cows and pigs and stuff like that. And so the reason why that works so well is because by training it on a data set that had these animals, it had to figure out these more advanced patterns. And so if you knew what those, like the fact that it already learned what these advanced patterns are, it was easier for it to distinguish, you know, what patterns exist for malignant versus non-malignant. And that's the idea of like kind of like using, you know, I call it bottleneck features. I think the curriculum talks about like extracting features, but that's the idea that you pass this data through here and you can say, oh, here's the filters, like, oh, it does have this weird swirl, or, you know, it has like, you know, some of this, you know, kind of like, I don't know what to call these, but like these different swirls and patterns and stuff like that. It has this kind of pattern. And then you take those, the vector of like all these different patterns, and you can feed that through classification. So maybe, I'm just gonna make something up. Maybe skin cancer that's malignant has more like this kind of pattern over something that's not malignant might have more of this kind of pattern, you know? And then you say, oh, okay, like, you know, basically from that neural network, that fully connected neural network, it can take the vector of patterns and say, oh, well, if it has these two patterns and like this much of these patterns, then it should be malignant. And if it doesn't have those, it's non-malignant or something like that. So that's the idea of kind of building up the features from a pre-trained convolutional neural net. Does that make sense? I know I kind of went through that pretty quickly and abstractly, but
yeah, that like the overview makes sense. For me, it's always on the when it comes to the implementation of the network and the like passing in the right parameters and features to make sure you get the best results.
Yeah, and that's a lot of fine tuning and stuff. And this is where maybe this is a good to actually talk about the notebooks that I kind of have set up already for like transfer learning. So this kind of leads right into it. And so the main idea for transfer learning, and it sounds like you already read through this section, so this will be kind of like familiar in review, but I also kind of talk about the ultimate situations. You can imagine like, this is the full CNN network. So pretend you train this CNN network on a very, very large data set. For example, ImageNet was, you know, a huge, you know, like neural network or CNN to train on many, many, I can't remember the exact data set, but it's a pretty big data set. Same thing with VGG19 or VGG16. There's also ResNet 50, very, very large structures that they literally took like days, if not weeks to train, you know, this huge neural network. Like it's many, many layers. Like I think the 50 represents in ResNet how many convolutional layers they have, or how many kind of like structures of not just convolutional networks, but like kind of like overall structure. So it's a very, very large neural network. So it takes a long time to train. So they had it trained and they actually released it saying, oh, here's the weights, here's, you know, the structure of the model, here are the weights that did really well in identifying these different classifications, right? And so I think it was like 1,000 different classifications too. So there's a lot of different things. So the idea here is that you can take something that's already been pre-trained by yourself or someone else on a data set and then apply it to your data set to figure something out. So that's really easy if your data set is very similar to the original data set. So imagine like if this data set was trained on farm animals and you feed it in a cow, or like you're like, oh, I want to see, you know, is it a cow or a pig? You know that, you know, this model is going to do pretty well because you've basically already trained it. But then you can say things like, well, what if I want to train it on like, let's say you trained it on farm animals. Like, what if I want to train it to see if it's a dog or a cat? Well, you know, maybe that wasn't the original, you know, data set. It never saw a dog or cat, but you can still use the structure because it's learned a whole lot about what animals are and the different kind of like features of animals that determine if it's a cow, a pig, a chicken, and whatnot. So the idea is that you can take that architecture and use it, you know, in your data set. And so it's really cool is that you can also use this when you don't have a very large data set. So usually you talk about neural networks, they love data. Like neural networks just gobble up data, you know, they just need all that stuff to really train. And the problem is if you have a data set that's only like 1,000 large, that's not a very big data set. And you might have an issue of overfitting on that data set and not being able to get results from that. So transfer learning can also help in the sense that you can learn off a really, really large data set and then take that data set or this model that you've already pre-trained and apply it to a smaller data set and get relatively decent predictions from it without having to like try to get more data from that smaller data set. So that can be really useful for, especially for domains where you're like, oh, like, you know, we don't have that many, you know, let's say we don't have that many pictures of skin cancer, you know, like for whatever reason, you know, the data set's just not very large, but we have a huge amount, you know, we have a really great model that does a great job in like some other domain. You can then take that and apply it to something that's smaller. Okay. So I kind of broke it down by a few situations. So this is more or less kind of like what those situations are. Basically, it comes down to what the original model was trained on. and how big your data set is. And if you have a large data set, but and it's similar to the original model versus a large data set, but it's different from that data. So think of like it was trained on farm animals, but your data set is skin cancer, images, like it's going to be different from each other, but you can still use this. And then also if you have small data sets, whether they're similar or different from the original data set that the model was trained on. Okay. So that's kind of like the 4 overall things. And I kind of broke it down a little bit. So I'll kind of go over this. So the main thing, like, if you think of like each of these situations, it's good to think about like, what is your situation, and then building it from there. And of course, you might have to play around like, what is a large data set? What is very different? Those are subjective. So you have to kind of play around with like what this looks like. But in general, this is kind of how it works down. So if you have a large data set and it's very similar, you can think of it like all you're doing is just fine tuning your convolutional neural net, right? You're basically just adjusting your model. And so the idea here is that we're basically using the layers of the CNN to detect low to high level features. So basically we're using all of this CNN right here, and you can see this is the fully connected neural network right here. We're using all of these features to say, all right, we're just gonna go ahead and like use those layers and learn from it. One thing we do have to do is we have to get rid of, basically all of these, we have to get rid of this neural network at the end, because basically we don't have, it's going to be a different classification. So imagine if you're classifying on like 10 different farm animals, but then your situation is, whether it's a dog or cat. Well, you're going to have to basically get rid of the neural network to do that. But right here is basically all of this stuff right here is outputting a set of features. Basically, what are the patterns for whatever image you fed through? So we can still essentially use this part and just feed those features, kind of like feature extraction, into this neural network and train this neural network here. So what you'll do if like it was a very large data set and you have similar data, what you can just do is essentially take a new neural network, put in a new neural network right here, this fully connected, so I'll call it FCN, right? Your fully connected neural network, put it here. You're going to randomize its weights, so you're all set to like relearn it. And then this stuff right here, you're just going to go ahead and keep it the same. So whatever the initial weights were from that like really well-performing model, you're just going to keep those weights there, and you're just going to go ahead and feed your data and have it retrain the whole thing, just like as if you were doing a CNN. The difference is that instead of retraining a full CNN architecture, you already have essentially some shortcuts. Basically, the weights are already pretty close to optimized. So what's nice about this is that because you have such a large data set, you don't have to worry too much about overfitting. So the idea here is that you can train this whole neural network and not worry about overfitting, but because you've already pre-trained it and there's a similar data set, these weights will probably be adjusted just a little bit. It's not like it has to like find the right spot. So your training speed will be a lot quicker. So instead of having to train it completely from scratch. Okay, does that make sense? Okay, and you can think of like,
quick question.
Yeah. Mm-hmm.
So in the diagram,
mm-hmm.
So this part, can you just explain
mm-hmm.
what it represents again? Because over here is the recognition of the features, right?
Mm-hmm.
I mean, sorry, the convolution phase.
That's right. So this is like the CNN part. This right here is that fully connected deep learning or neural network part. So this is what I call the FCN. So if you imagine, I think I have another, I'll probably change this up a little bit. But if you remember this part right here, this is like getting the convolutional neural network part. And this is kind of like the fully connected neural network over here. So it's kind of like you get these features. If you, let's see if I have an example of this. I don't have a, well, I'm trying to, here, I'll pull up one of my projects I had before in the past. If you like were to code this up like in Keras, right, you would have something like, here's our convolutional neural networks, right? And then you would have your dense network. You might have like multiple layers for your dense network. Basically what it means that you would not change any of this part, but you would change out this part right here. Does that make sense? Okay.
And the dense portion in the network is the...
Mm-hmm. This guy right here.
Yeah, does it point towards the input layers, or is that upper layer, or is it something completely different from that?
Right, yeah, this will actually point to the output of your convolution parts. So your convolution will take in an image, right? whatever that image is. I'm going to use image, but no, you can use other things, right? You feed in your image here, and then it takes that image and uses the basically different filters, right? These convolutional layers to figure out these parts. And basically at the end of this convolution, it's going to have a vector of features represented by like this guy right here. So this is essentially like a tensor, right? It's basically a bunch of different features. And that's going to be put into just a vector, right? And with that vector now, we can feed that into just a normal multi-layer perceptron network, or we call it a fully connected network. And that's what this dense layer is right here. So if you go all the way back when you first learned about neural networks, it looks something like this. Let's see here if I have this. Like you might have something like multiple layers, like a dense network, dense, and then this is like the output, right? You would have something like this. You basically copy and paste that into here, depending. So like this here, I have an output of 24 for my dense network. If I had like only 3 classes, I would go ahead to get rid of this and change this to like a dense network of 3, because I would have 3 parts. And note that I only have 1 layer here. You could have multiple hidden layers, and that's what this diagram looks like. That's why there's 2, 1, 2. This would be like 2 hidden. This would be like almost like the input layer, if that makes sense. But you're inputting it from the CNN, and then you'd have a hidden layer, and then your output right here.
Oh, okay, so with CNNs, so pretty much a lot of the big difference between it and the initial neural network we learned is that it has this prephase where it takes this multi-dimensional representation of data, strip it down into a flattened version that's one-dimensional, then passes all those features in, and then the input layers of the dense network itself, the hidden layers, they take in all those vectors and try to calculate ways to say, oh, okay, this is useful, this is not. And from there, then it spits out the output.
That's right. That's right. And I think that's,
Winning.
yeah, good job. Yeah. You like, and that's where you can kind of see on this visualization, you can see like, it's almost like little squares. It's like that vector, right? It's like taking that vector and doing the neural network, stuff essentially in here until eventually it gets this classification. Cool. Yeah, perfect. You had it right on there. And that's where like transfer learning, can be super useful. So that's where in this situation, if we have a large data set that's very similar, we can say, all right, basically keep everything the same. We got to change out this neural network because it's structured differently, right? Like this neural network needs to be done for like, let's say 2 classes versus instead of 10 classes. So you're going to put a new neural network on the end. That'll be similar to every transfer learning part. And then you say, okay, we're just going to go ahead and retrain this whole network all together because we have such a large data set and it's really similar. So we kind of have a little shortcut. So we don't have to like adjust the weights, a whole lot. We can just kind of tweak the weights essentially. And then we get hopefully we get a pretty decent like result within a short amount of time. Okay, cool. Awesome. So it makes sense, at least for this part. And I think you got it down to like the overall structure too. So that'll be useful as we kind of go into the different situations as well. So, all right, so the next kind of situation is like this large data set, but with different data. So in this case, our main thing is like, well, it's going to be it's very large, so we don't have to worry about overfitting. So we can kind of train the whole network altogether. But the problem is that it's very different data. So what we want to do, basically, we don't want to kind of like, there's a couple situations like there might be, because it's so different, it might be worth it just randomly initializing these weights in the convolutional neural net. We still have to replace this neural network at the end here, but the convolution, might have to just randomize it because it's just not going to be very good at the initial weights of the CNN layers, just might not be very good for this data set since it's so different. But just kind of a quick note to that is that it might be worth it might actually be worth just keeping the same weights. So even though the data sets are very different, sometimes it actually might work faster just keeping that weight. So maybe like it's very different, but it's close enough where it does a good job. So the overall kind of consensus, like the way you might do this is you basically have the same model architecture, get rid of this FCN, put in a new one, right, for your specific data set, right? So your classifications. And then you're going to randomize this guy and then keep this guy as if you're doing this large data set with similar data, feed it through, see how well it works. If it doesn't work very well, then you might actually have to go ahead and randomize all of these guys in here and then retrain the whole network again. So the idea here is that you might get lucky in the sense that maybe the weights in here do a pretty decent job of being similar enough. But other times maybe it's just so different, it's just like, oh, we just might as well randomize. It's more likely for us to get a better result than wait for it to untrain itself from those original weights. So that situation might be something like, you might think like skin cancer in animals are very different from each other. But if you try it out, maybe, the overall patterns that it found from detecting farm animals or whatever, right, actually work really well with skin cancer. So you actually get the result really quickly. However, maybe you try to run this and you find out it just takes a long time and it's not doing very well within the first few epochs. So you just might as well randomize all of this stuff in here and then retrain the whole thing. Okay. Cool. And you can kind of think this kind of like, you either fine tune it as if you were doing it like the large data set, which is kind of like you keep all the weights here and you just kind of like let it run through, or you can basically just completely retrain this convolutional neural net. Right. And again, the reason why we're retraining all of it, note that like we're retraining not just this weights over here because it's a new fully connected neural network, we're also retraining all of these things in here because we have a large data set, we don't have to worry about overfitting. And that's what could be a big difference when we have a smaller data set. When we have a small data set, we have to worry about overfitting. And so in this case, for like a small data set with similar data, so imagine like you have farm animals and you want to train, is it a dog or cat, right? So those are like relatively similar. The idea is that you want to use basically this high level and low levels of the CNN and then retrain it. But the thing is, we have a very small data set. We don't want to accidentally overfit on this smaller data set. So maybe you only have like 1,000 pictures. So what you do to make sure this doesn't mess up, we can actually freeze the weights on here. So they don't update these weights. Like don't try it. Like we're going to train this network, but don't try to update these weights. Keep them exactly the same they are. And then just make a new neural network at the end here and retrain these weights down here. And that way we can avoid overfitting, but we still get basically all these high level and low level features and their high level features. Basically think of like, if I go back to kind of visualizing it, these would be like the low level features, like very basic patterns to high level features. And that's because we can use these high level features because they're very similar.
Okay, so question.
Yeah.
So like you made the example of a neural network trained on identifying farm animals, and then it was used on skin cancer, and it did really well. So then what would, because to us, like, at least to me, like, yeah, a cow is a cow, a pig is a pig. Skin cancer is completely different. But in the overall scope of things, since the network doesn't see an actual image and process it as a human, but as tensors of zeros and ones, how would we recognize different data? Or how would it recognize data as being different in the network? Is it something it doesn't do, or it just depends on patterns?
It is a tough one to say exactly what is different from each other. And this is where it's not so much the content, but of saying, how do we determine these things? And this is where it's tough as like a human, because we like, we do it automatically. We look at something like, oh, that's a dog, like duh, right? Like you don't need to think too hard. But the big thing, what we're looking at is essentially, what are the visual patterns for determining, an animal versus determining what kind of skin cancer is. And so, for example, like I kind of mentioned a little bit, like, like these later layers of like, if you train it on just animals, you might see things like fur, whiskers, eyes, like those kind of patterns will pop out in this filter set. But if you start using it to identify, I'm just trying to make something up on the spot, like different plants, right? Those patterns might not make a lot of sense. Like the patterns that we found from the animals might not really be helpful in determining, is this an oak tree versus a maple tree? Let's just pretend that's like the classification. And so the idea is that's like, well, okay, if it's different, you might have to basically reset, these filters essentially. But it's kind of tough for us to do sometimes, because sometimes it's like, oh, it turns out like us trying to figure out what, something is, like what kind of animal it is, might actually teach us enough to identify different patterns that appear in non-animal images. So for example, like maybe your network wasn't actually as deep as you wanted it or something like, or needed it to be. And maybe it's able to find more of these kind of like overall patterns. So like, I believe this is from ImageNet, and you can see here, there aren't really like, at least from this set of filters, there doesn't seem to be like very specific things that are about like fur and stuff. And that's because ImageNet had 1,000 different kind of classifications. They were animals, they were objects, they were buildings, trees, all these things. So it had to build a very general set of patterns. So sometimes these neural networks that are very broad have to find more broad patterns instead of very specific, like I said, like eyes or something like that. So that's kind of like the overall thing. And an honest truth, you know, what makes it different versus not different, it's not really easy to tell. And sometimes it's just like trying it out and seeing what works well. But what is nice about transfer learning is that you can speed up this process. You don't necessarily have to wait around. You know, like if you train a huge neural network, it can take a long, long time. Transfer learning can help speed up this process. So you can check it out, you know, after a few epochs, and those were relatively quick because basically it was already pre-trained. So that's kind of the idea of it. Does that kind of clarify a little bit of what you were thinking about?
Yeah, that one made sense.
Okay, yeah. Yeah, it definitely feels very like vague. Like I will give you that. Like different versus similar is like, what does that mean exactly? Even like small and large, that's like, when does a small data set become a large data set? It's like, it's not really clear either. It just all depends on context and honestly, just what works well. So yeah, cool. So cool, but everything else understood, small data set, similar data, kind of like what that procedure looks like. Does that make sense to you?
Yeah, yeah. So will this notebook be available just as a reference?
Yeah. So here, I'll show you a little bit. Sorry, human dog. Oops, I'm on the wrong page. I'll send it on, I'll put it on Slack too. But this repo here is kind of like where I put all my notebook stuff in here. And let's hear, this will specifically be in the deep learning. And then I think actually, you know what, right now I have to push the edits, but it'll be under transfer learning right here. And you can see those notebooks, transfer learning here. So that way you can kind of find it.
Okay.
Yeah, and I try to keep all these resources too. So like, for example, I mentioned about some of the convolutional neural networks. I kind of reference a couple of those images and notebooks. You can find them here too. So that way you can kind of go through and stuff like that. And I try to, you can see in my README, I'm trying to keep things a little ordered so that way it's a little bit easier to find like this too. So it's a work in progress. So, you know, to be handy. But yeah, I'll send it here. I'll send it to you right now so I don't forget. Where is my bubble? That's just the overall repo, so you can kind of go through it as needed.
All right, cool. Thank you.
No problem, of course. Yeah, all right, so then I'll talk about the last transfer thing. I just want to make sure we can get through this part. But good questions. The last one is like, if it's a small data set, but it's different, right? So this is kind of like the worst case scenario. It's like, oh, we're trying to identify plants, but, and it says we only have 1,000 pictures, but we only trained it on farm animals. And it's like, what do you do? So this one's a lot harder to deal with, obviously. But the idea here is that we use the CNN only to find low-level features. So the idea here is that you're trying to find those patterns like this guy up here. So we're only going to use it to, sorry, my dog's being, it's kind of rainy and she's being all, like, I want to sit in your lap. Just ignore her face right now. Hope you don't mind. But these basically smaller patterns right here are basically like the things that we want to identify, but we don't care about these higher level features because they're going to be very different from our normal data set, right? So we're going to go ahead and try to ignore those parts of the CNN and only look at these low level features. So what this basically looks like is that we're going to remove the end of the pre-trained layer. So we actually completely remove like this set of layers. And note that I say remove layers. How many layers exactly? Well, it's not really sure, right? You're gonna have to figure that out, like maybe doing some visualization, maybe just testing it out and see what works. But you get rid of these end layers here and then just keep these beginning layers and then pass your data through here. So you still will freeze up this layer and this layer because we don't want to overfit, right? So we'll still freeze this part, but then we'll get rid of these and then completely pass it to a new fully connected network. So if I kind of just draw on top of here, just to kind of emphasize my point, is that you will get rid of, like, let's say, like this layer, get rid of this layer, right? freeze this, right? Freeze these layers. And then this is going to be a new fully connected. And then what will happen is that when the image gets passed in, so let's say we have a new image, I'm just going to use a different color so I can emphasize. Let's say we have our image here from our small data set. This will get passed through all the way through here. And then this set of patterns will then get passed over to this neural network. And then this neural network will pass it through here. Okay. And so that's kind of like the idea, like for your small data set, but very different from the original data set that you modeled with. Okay, cool. All right. So just overall, oh, I think I showed a little, I have a little example here. This is just a different notebook I have that I had done myself. So this is what I was doing in this project. Let's clear this out. Okay. Thank you for being right here. Basically, this is I was using, if I go back, you know, I'm just gonna pull it up. Sorry, I'm stuck what this project is. So this project was essentially taking hand shapes from American Sign Language. So I'm gonna try to put my dog down. So there we go. All right, so we had, I think I have this as the paper. Here it is. I'm just trying to pull this up so you can see a little bit what this is. But basically there's different hand shapes like A, B, C, D, E, F, you know, for American Sign Language. And basically taking images like this and trying to say, oh, is it an A, is it a B, is it a C, is it a D, you know, those kind of things. And so this process here, I kind of showed a few different techniques in this notebook itself. And so the first thing I tried doing was essentially just making a, you know, doing the whole process, right? And just building a CNN from scratch and just doing the basic stuff and seeing how well it produced and like how well it works. So you would be able to read this through and pretty much more or less understand what's going on. When you evaluate this though, it said something like about like maybe 50, maybe 60%. I think it was less than 60%. It's like 50% accurate. And so it wasn't really the best kind of model overall. So then you can try doing, I tried doing transfer learning. So I actually did transfer learning with VGG16, and then I did things with VGG19 as well as as ResNet 50. So ResNet 50 ended up being like the best results. But you can see here is that what I did on transfer learning here, basically I took my model. Hey, sorry, my dog's kind of going at the door. I basically take this part. And so this is, instead of like taking this whole model, I froze it and basically just passed in. So if you look back in this transfer learning, I basically passed in the data through here ahead of time. So I took all my images, passed it through the model and created basically a new data set, what I call the bottleneck features. And basically they're just the features of like, what happens if I put my image through this model that's already pre-trained, keep those, essentially this tensor of like, or vector, you can think of it as a vector, representations of my image from this originally trained CNN, and then trained a neural network off of that. In fact, you could even use a CNN to train off of that too. So you can kind of say, okay, I'm taking off these layers here and only train it with these layers, or sorry, create the bottleneck feature from these layers, and then create a new CNN that would take those layers and try to determine more. So you can kind of do some really interesting kind of play around with, see what works. So that's kind of like what goes here. But just to kind of emphasize how useful this was, this ended up being the most accurate when I used a very large neural network, created those bottleneck features. You could also have just done it as the whole model, but I just created bottleneck features so I could speed it up the process and then train off of those. And that actually ends up being much more useful in a lot less time than trying to build up ResNet 50 completely all by myself and then train it from there. So yeah. So I just kind of put this link in here, just kind of show a little example of like what this looks like. So you can see here, basically this is my new model where I actually take a CNN and then use a dense neural network right here and try to put the output. But the input in this is kind of interesting. It's not the original images, it's actually the bottleneck features, which again, the bottleneck features is really the features extracted from feeding this first initial pre-trained CNN. Okay. Cool. Okay, makes sense. I just kind of want to show you a little bit like how that would be used in practice.
Yeah, so the overview makes a lot of sense.
Okay.
Yeah, I'll be honest, I'm just dreading now that we're about to go into capstone. how do I use this, and then getting everything else complete for graduation. So
I'm sure you'll be fine. My big recommendation is, instead of trying to shoehorn a specific skill or methodology, is think of what the business problem is, or like your stakeholder problem. You know, what is your question essentially? And then think, okay, how would I get to this answer knowing the things that you know? I think that ends up being a little bit easier and also a little less intimidating versus like saying, how do I get a CNN to, into this problem and stuff like that. Yeah, I think one thing I'll suggest is that if you do something like a CNN or a deep learning set, if you can do transfer learning, like if you have the opportunity to use transfer learning, I highly recommend try using it because it tends to work really well. And it doesn't take too much effort in training time versus like literally training for hours and hours and hours for one CNN, where transfer learning can do it like within an hour. And you're like, oh, wow, that worked pretty well. And I didn't have to do, like try to have it trained for a long, long time. So yeah. Anyway, yeah, that's kind of overall, at least from the curriculum standpoint of like transfer learning. You can see it's a relatively short section. Definitely go through, like if you haven't already, go through that curriculum, lab and everything like that. I think you'll do a pretty good job. Yeah, I will point out there's a little notebook I have at the end here. It's not necessarily related to the curriculum, but it's kind of an interesting use of like, I think it kind of can give you some details of like what transfer learning is like, and like kind of imagining what we're doing when you're transfer learning. And it's called style transfer. So the idea here is that you take a neural network, a model architecture, and you feed in a picture, and you feed in another picture essentially, and you try to transfer the style onto a content image. So you can imagine transferring the style of a, this is like Vincent van Gogh's Starry Night onto like Mona Lisa, right? And you can see this the result here. And I won't go through the whole thing. I have some links to different tutorials. There's a Keras implementation. There's also a PyTorch tutorial that's pretty good, but it's in PyTorch, so you might not be familiar with it. But you can kind of see some similar things. So here, I just kind of, this is a post I had before, is here you can kind of see different images. So you can see different art images, and like you can see there's an overall style to it. And you can take down and say, okay, from this specific part of the CNN, use the filter and apply it to the original image. And so you can see here I have like, this is a picture of my dog, and I applied, that image over to here. You can see different parts, like the different styles being transferred over to that dog and stuff like that. So this is much more of like an art kind of project, but like it's kind of helps you visualize what's going on with a transfer learning and CNN. Yeah.
So that's pretty much how like on these different camera apps, they have these filters. Oh, that's cool.
Yeah, it might have different strategies and like how they do that, but this is one way you could possibly use this. It turns out this is actually, this specific technique is a little hard because it does require you to basically train the neural network to basically say, you define a loss function, and that loss function is going to determine, say, how different is this picture from this content in the original style. So it turns out it's probably not what most phone camera apps use, just because it takes a lot of effort to do it. But one kind of nice thing is that kind of shows you a little bit of how to transfer information over it. You're basically saying these part of the CNN are really like useful in determining like, this overall structure. So it's finding those patterns and taking that pattern and applying it to the original content image. So there's a kind of quick other stuff. Here's where I took the same same style image and applied it to different content images. So you can see here, here's the style image, here's the content. So apply the style onto here, and you can see like what kind of it saw. I said, oh, obviously I emphasized more of this color onto this part. You can actually see I have a little GIF here. I couldn't download it from my Twitter post, but you can see here, like as it gets more and more, it's basically cycling over and over and over and over again to make it more and more stylistic to that original image. So you can kind of see there's an overall process. Basically, it's trying to minimize this loss function that's going to make it similar to that content, but away from, closer to that style, but also similar to that content. So there's a loss function we kind of build into this part. So anyway, and then you can see here's the same style image different content, and you can kind of see here. And this is kind of nice because you can actually see a little bit of like what it's picking up. For example, it's maybe from this image, it's not necessarily the color, like even though the color definitely is part of it, it definitely seems like these streaks and kind of like the style of this water paint kind of thing. And you can see that kind of evolve into this picture as well. So I have some code here in this notebook. But the reason why I kind of bring this up is because this actually brings you into like cycle GANs. So GANs, generative adversarial networks, which is kind of becoming more and more a common and more, just a lot of different applications to like generative adversarial network. This kind of leads into cycle GANs, which is kind of taking the same idea where you only have two pictures here. And essentially what you're doing, you're kind of taking the style from here and applying it to here. So CycleGAN kind of does something similar where you basically take these pictures, for example, it finds out what is inherent to, for example, the zebra and tries to apply it to its original image. So you can see here, this is actually from this original, actually this is from a tutorial that I link here. But basically the idea here is that you actually have, it's a different kind of technique, but similar thing. And so if you're interested in like generative adversarial networks, I think it's easier to go from, oh, I understand what CNNs are. I can see how this transfer kind of goes through. And then say, okay, from there we can see how CycleGANs work. And then from CycleGANs, you can probably get an idea of what an adversarial network is. So I just kind of throw it in there. So you're welcome to kind of go through those tutorials. I have some links in there. So yeah, but other than that, that's kind of all I have for you. Any overall questions? I know it's kind of, we're about right out of time, but I don't know if you have to go somewhere.
Sorry, I'm just pulling up my notes from this section.
Yeah.
I think for the most part you answered them. So for the convolutional network, in the section it spoke about the convolution base. What exactly is that? Is that the information contained from the pre-trained network, or is that something else?
You said the convolutional base, right?
Yeah.
Yeah, so that probably is referencing the fact that, I'm gonna go to this one, no, not that one. This overall model structure that can also involve just the weights. So that's kind of like you have the structure first of all, but you also have the weights of saying how much should each of these, parts be, adding up to the final result kind of deal. So the convolutional base probably is referring to the model architecture in the weights that are built into that architecture from pre-training. Does that make sense?
Okay. And what's the difference between feature extraction and fine-tuning? Because in the curriculum, it says that they both have similar operations, but fine-tuning differs in that it only freezes weights or something like that.
Yeah, so fine-tuning really is like basically like this larger data set where essentially we take the same structure and we keep the weights that were previous on there, and we're just we're training the whole model through. So we're allowing the weights to be adjusted. So that would be kind of like fine-tuning, where feature extraction is closer to kind of what I said, like the bottleneck features for the smaller data set situations, where essentially you freeze this guy here, and basically it means that you aren't training the CNN anymore. In a sense, you're using the CNN as a funnel of saying, oh, give me, I'm going to put this data in here. You're just going to give me whatever the results are supposed to be, and then I'm going to train off those results. Versus the fine tuning where you say, okay, we're going to adjust the machinery to give me the results. So it's like a subtle difference, but the main idea is that fine tuning allows you to like modify the weights, and feature extraction, or I call it bottleneck features, basically you're freezing these weights in here and using the results. So basically you don't use the data to train parts of the CNN anymore. You just use the CNN to give you results and then train off of those results. Okay, that makes sense?
Yeah, that makes sense.
Okay, cool. Yeah.
Yeah, I think that's pretty much it for me, at least with those two.
Awesome. All right. Good. Well, I hope, again, if you need that repo, I sent that repo through, what's it called? Through Zoom. I do have some edits I need to push, I have to merge it with the master here, but that will be done probably later today. So if you're looking for it, just know it's gonna be there. And it's mostly done in like this deep learning section and stuff like that. And feel free to use this however you want, right? And if you find mistakes too, like definitely let me know or do a pull request. be useful. But yeah, hopefully that kind of gets you to a good spot. I know you're kind of getting close to the capstone project and everything, so I know that's pretty exciting.
Yeah, I think it might be next week.
Yeah, that's pretty exciting. I mean, you've been in here long haul, right? Was it about 5 months? So you guys are kind of like on that last part. I have a cohort that's just finishing up right now, and they're all really excited. Like they're also going like, oh my gosh, it's like a week away before we're finished. Like this happens really fast, but it's also really exciting. So yeah.
Okay.
All right, Ricky. Oh, I guess I'll stop recording here, so I can make this available for everyone.